All right, so overall, looked like you guys did pretty well with the exam. So we're going to move into the topics. So before the exam, we had started talking about Bode Plots, and DB was part of that. And so I just wanted to kind of readdress a couple things to be prepared kind of for the homework. So the first goal of today is going to be understanding characteristics of a sinusoid, conversion between dB and volt per volt, find a transfer function of a given circuit, and then use that transfer function to be able to create the Bode plot, which we'll again go into what the Bode plot is in a second. All right, any questions about what the goals are today? Let's start with signal characteristics. So a sinusoid would look something like this, where you have peak to peak is the top and the bottom. Amplitude is if it's the peak from the center. So if peak to peak is 8, the amplitude would be 4. So in some of the examples I gave in the lecture before, we had the exam. This can be a shifted sinusoid. So you would still do the amplitude as a halfway point between the top and the bottom, even though it could be shifted by a DC constant value. Period. Time to repetition, frequency 1 over the period, omega is 2 pi f. And then if I was to, so I think we're going to just skip phase shift, finding it from the graph this time. So from a graph, you're going to either have to identify, is it leading or lagging by 90 degrees or 180 degrees? So pi halves or pi. So just being able to look at a graph to see that difference. And I'll show you in a minute how to, well, I'll do it right now. So phase is going to be, so if this is a cosine, what should the value be at 0 for the cosine? Should be 0, right? If it's, or is it 1? Yeah, it should be 0. So if it's not 0, which is the case here, you can see like, well, it's not crossing at 0. So you're looking for the difference as far as how far is it shifted over. And so here you would look at the shift over to this value to determine like, okay, how much of a change is that going to be? So wherever it should be at 0, except for it goes up, so it's going to be, this is actually going the other way. So I didn't describe this very well. Let me try that again. So it's wherever it should be, so it should actually be at this time frame is where you should have 0. So here at 2, and here at 2. So this difference between here and here would actually be your delta t. So if it shifted by 90 degrees, instead of having it start at 0 here, it would be 90 degrees would be that it's peaked right here at the top. Pi, sorry. No, it's not. Okay, I'm just gonna stop talking for a second. Sorry. Anyway, that delta t shift is what you use to find the phase change. This is not a good example of the sinusoid. So let me pull up. So looking at your homework, if you were going to be describing this in the terms of cosine, this would be shifted over by 90 degrees. So instead of it being, I can't write on this one. So instead of it being, I can't say the right words. Anyway. Wait, cosine of 0, 1 or 0? It is 0. It's 1. Thank you. That's why I'm confused. Okay, so at 1, that's why I'm like, wait, it's not registering. So the peak here is at that first, I wish I could draw on this. And so between 0 and that point is your shift. And that's a half of a cycle, or a fourth of a cycle. So then it will be, so a full cycle is 2 pi. So that little period is going to be pi halves, so over 90. Okay. Hopefully that finally came out correct. Let me go back to this one. That's why that wasn't making much sense here. Okay, so it will be between here and here. Okay, so there's your shift of delta t. So you can find if it's not 90 degrees and you're like, well, what is it? You measure it from 0 to, for the cosine, it will be to the peak, the first peak of 1. And so that shift there is what you use for delta t. Okay, go ahead and try and find for this particular signal, amplitude, period, frequency, angular frequency, and then the time domain expression. So it was, let me move it down to you. So it's at 0.5 milliseconds is that first peak, and then 3.6 milliseconds is the second peak. It's just hard to extrapolate that on that graph. So I could write it up there for you. Oh, yeah, you could just put V for the phase shift. Somebody changing it? Okay, one more minute.
Would you do for the type of meeting especially? Yeah, I'm guessing you have to like is it in terms of okay, so that's before we do the transfer. Wait, I'm still with the text. Well, I don't know, I'm guessing. So wouldn't it just be exiting? I can't.
I'm seeing some differences in units, so
That's
let's go through this.
it's the only thing with time in it.
Okay, so amplitude is just one peak. So if peak to peak is 8, then it would be half that. So in this case, it was peak to peak was 8, so 4 amps would be your amplitude. Time period is the distance between one peak to the other peak, which was 3.6 minus 0.5, so 3.1 milliseconds. And then you take 1 over 3.1 milliseconds. So this is where I saw a couple answers. Make sure that milli is multiplied in there. That's 10 to the minus 3. I also saw this on the exam that there's a few of you do make sure that you go note what you did incorrectly, and if it is units, that you're getting very familiar with milli and micro. I did actually see quite a few errors with the units in there, so do make sure to go and go over those again to make sure you understand the units. So with this at 3.1, so this is 3.1 times 10 to the minus 3, and that would be 322.6 hertz. And then 2 pi times that will be 2027. What's the units for omega? Thank you. So hertz is frequency, and then omega will be radians per second, which is angular frequency. So this is angular frequency. And the reason I'm pointing this out is because when we move to Bode Plots, the default is going to be this unit. And so you want to understand if you've measured something in hertz and you want to compare the two, you'll need to convert it from radians per second into hertz to do a comparison. All right, so don't worry about, for now, the phase shift. So plus or minus phi would be what you would put on there. And then to write this, you would take the amplitude for cosine omega, which is 27t plus or minus phi. Since phi could be negative, you could have written either one of those. All right, questions about signal characteristics? So you'll have to do this on the homework for one of them. All right, converting dB to volts per volt. So last time I introduced the Bode plot, and we talked a little bit about this dB. So the dB is a unit, decibel. And the decibel is going to be used to understand the magnitude. And it helps to understand when things are really big numbers. When we graph it, you'll actually see from some of the number calculations like, oh, that makes sense that we can do things in dB and we can see the trend of what's going on or the characteristic of what's going on without having these really big jumps in numbers. And so it gives us more information when we're looking at the graphs themselves. So to convert from volt to volt, when we solve a circuit, you are going to be in default the unit of volts per volt. And when we want to graph it in that dB. So we need to convert from volt to volt value to dB. Yes?
Is the V out and V in, should we relate that at all to like the gain that we see in op amp, or is that completely separate?
It's exactly the same.
It's the same, okay.
So an op amp is made up of a transistor, well, lots of transistors actually in there. And those transistors, you analyze the circuit, you're going to get an output expression in terms of the input. And then it also has all of those S's based on the frequency response of what's going on. So you actually ignore all the frequency response issues, and to find the mid-band gain is going to be the number that's kind of out in the front of the expression. And that will be like value of 10. That will be 10 volt per volt, and then you can convert it to dB to have the actual gain of the amplifier.
Okay.
So yep, so it is the same as a gain.
Okay.
Is V out over Vn. We're going to talk about it as far as filters, and so it gives us the Bode plot, and then from the Bode plot we can determine what type of filter it is.
Okay.
So that's how we're going to be looking at it. Okay, so expression for conversion is this 20 log V out over Vn. That gives us the unit in dB. So if we have that number, we just take the log base 10. So this is log base 10 of that times 20. To convert, say we have dB and we have some magnitude graph that we're given. So if you guys want to, on an op amp data sheet, you can actually go look, and in the back of it there'll be this Bode plot, and you can see, oh, there's dB on one side and voltage, and it will show you a range, and then it will like cut off after that frequency. So you can look at that now and be like, oh, I understand this is now in dB and this is over different frequencies. So converting from something like that, where it gives you the dB value, you want to know with no feedback, what is that gain value going to be? You would need to take that value, divide it by 20, and then it's 10 raised to that value. So that's how you convert it back to volt per volt. So go ahead and try and convert these. Just going to relabel this. So this will be V3 and this is V4. XDB1, the XDB2, those are just the variable names for that to find. So XDB1 should be the DB for 401. Those are just variable names. Like somebody asked me that question. So that green is not very easy to see. So let's see, find a different green.
Oh, yeah, okay.
Looks the same. Is that better? Still no. Okay. Oh my. Okay, so it's 10 raised to the dB number over 20. This is how you go from dB back to volts per volt. So this will give you volts per volt. All right, so for the two people that decided to answer with that, thank you. So 4 will be, 12.04 thing. There we go. Plus 12.04. And then a 1 over 4 is going to be a minus 12.04 dB. For 46 dB, it's approximately 200 volts per volt. And for the minus 46 dB, it was 0.005. I think it's 0.005, yeah. 0.005 volt per volt. Okay, so you're gonna have to practice this again on the homework, so make sure you're able to convert back and forth. One thing I want you to take away from this is, what does this 4 mean here?
Yeah.
Thank you, V out. And what does the 1 mean? So what does this mean to have a positive dB number? Is V out in comparison to V in is what?
Bigger.
Correct. So V out is bigger than V in. So in a case like an amplifier, you would have a gain, and that means like, yeah, this has a gain to it. What about this one? What was the top one? V out, and the bottom is V in, so what does this one mean? It's what is called attenuate. An attenuator, or reduces the input. So if I give 4 in, I actually got 1 out. So it reduced that input, it attenuated that signal. So reduces it. So this was one thing, if you remember when we did the voltage divider, there was one example where the voltage divider reduced your input, which was not what you wanted. So we put a voltage buffer in there to keep that signal the same from one point to the other point. So that was an attenuation is the other name for that, but it basically reduces it. So here we see, like for 46 dB, that's actually 200 volts per volt. So as you get up in really large numbers, the dB in comparison is actually a lot lower number. And then a negative, which makes sense, goes to a decimal or less than 1 value. All right, questions about conversion, dB to volts per volt? Yes.
This is kind of random, but like, why is the coefficients of like the equation like 10 and 20? Is there like any significance for like those numbers? Or?
So Alexander Graham Bell, he noticed that in his hearing, he was like, you know, I hear like linearly. And so he made the scale.
Oh.
And he is the one that decided this is where it's going to be.
Oh, so it's like more
And
like...
he noticed it was a log. So I don't know why 10 and 2, I don't know. But it was log based.
Oh.
So he realized that it was log based when he started measuring and comparing that. So yeah, it just basically log. And it just happens to be log base 10. So he decided that one. All right, any other questions? Okay. All right, so to go to the next step, which is where we actually solve the circuit, and then we're going to draw the dB magnitude now and the x axes. I wanted to just go back and remind you that with this, we're looking at solving in the time domain for one capacitor or one inductor. We had a differential equation of first order, right? So what happens when we get 5 capacitors or 5 inductors in the circuit? What order would we have if we have 5 of those elements in a circuit? A 5th order differential equation. Anybody want to solve that one? I'm seeing lots of like, no way. So, very nice thing for engineers is that it was realized by Laplace and Fourier that if you move from a time domain into a frequency domain, you can manipulate those instead of with derivatives and integration. You can multiply and divide and add and subtract so much easier. So that's why we move everything from this time domain into this frequency domain, because it's going to be way easier to solve. We can have as many elements as we want that are differentials, and they're going to be able to be solved in that frequency domain.
So for context of the frequency domain, is the multiplication, is that the derivative in the time domain, or is it, I can't remember which is which. Or am I just getting that wrong?
So it actually doesn't even matter to remember which one is which, because we're going to just convert the elements, and then we're going to just treat them like we've done all of our other techniques. So you don't have to remember, which is good that you're like, I don't remember right now. So you don't really need to remember. I mean, there's a table you can look up, and I can show you really quickly. I think no, it's not on that one. I don't remember which lecture it was. Maybe I don't remember which lecture I did this in.
Yeah, I know
But
which
anyway.
table you're talking about, but
Oh, here's some of them. Oh, I thought it was on this one, but so when you have like the first time derivative, you change it over to the Fourier. So this one's the Fourier tables. There's some for Laplace too. You have a multiplication of S with it. So you get S times the F of S.
okay.
And then minus an initial value. So, you can do it that way. Integration is 1 over S times the F of S. And then Laplace has the similar kind of table. So you can, anyway, sidetracked on that one. Let's see, 15 version 2. Okay, so once we get a solution, say we have V out is equal to some expression in terms of S or J omega, and all we have to do then to find the time domain is convert it back through an inverse, either Laplace or Fourier, depending on what we originally used. So if we convert it into the frequency domain with a Laplace transform or a Fourier transform, then we just have to make sure we use the same one on the way back to the other conversion. So this makes it really nice to be able to solve a circuit without having to do a fifth order solution. And so one of the things we're going to do is convert our elements from the time domain into the frequency domain. So a resistor goes to resistance, a capacitor goes to 1 over CS, forgot the C in there, or 1 over CJ omega. And for an inductor, it's just SL or J omega L. And the only difference you see here is between the Laplace and Fourier is that S is equal to J omega. J omega usually denotes having the omega in there is usually Fourier. And so those are the only differences between the two. But you treat the elements themselves the same. All right, any questions so far about this? Okay. So now when we look at like a frequency domain, so say this frequency is at 3 hertz for this signal. It has an amplitude of 1. This is going to be, and we can describe it by cosine omega t minus some phase. This one has 0 phase. When we draw the magnitude, it's going to stay the same magnitude. It's just going to have one value, though, at that specific frequency. So in this case, this will be 3 hertz. So our x-axis is going to be in frequency, which is hertz, or omega radians per second. And to convert, you're just going to convert if you are like, oh, I know my hertz, I know the frequency of the signal I have. You would just do omega. You just do 2 times pi of that to get the omega. For the phase, there's 2 components when you draw this in the frequency domain. So there's a magnitude component and a phase component. We're not going to worry about the phase component right now. You're going to learn about that if you go on into other classes such as classical mechanical control. I think it's like MEN 5200 or 5220, one of those numbers. So you'll look at that one and the effect of why do you want the information from the phase. Most of the time it's with stability of a system and making sure a system is stable by how much the phase is changing. So for us now, we're going to look at mostly the magnitude. So this is for one frequency, one value is on this graph, okay? What happens when you have two signals and you combine them to give you another signal? So first signal, second signal, the third is the addition of those two. So it looks like that on an on an oscilloscope. And then if we're moving that to just the magnitude frequency plots of those, the first one would be described by this first graph, second one by the middle, and the third one just has the 2 peaks. Really easy to look at this and say like, oh yeah, at 3 hertz for the first one, that has the most contribution of, that's exactly where the signal is. Same for the second. And then the third just shows you within this I have 2 main frequencies, and the higher one has more amplification in it or has higher signal in it. So what happens when we have like a noisy signal? One thing we may want to do is remove this to be able to get back to a normal signal. So with a noisy signal, we can use a filter. So when we looked at this noisy signal, blue doesn't show up very well there, we see that we have that peak at 3 hertz still. So we can build a circuit where we want to just pass only the 3 hertz and then remove the other signal. So we want to create a circuit that gives us a Bode plot. Oh, that was not a very good drawing, sorry. That's going to look like this, that it will give you attenuation. So sorry, this should be under 0. So below that 3 hertz, it's going to have attenuation. And then at 3 hertz, it's going to pass everything you want to pass. And then after that, it would then attenuate it again. So we would want a circuit to create a Bode plot that looks like that. This is a band pass filter. The other types of filters is there's a low pass. And with a low pass, it's going to pass everything till it kind of reaches a certain frequency, and then it's going to attenuate everything after that. Sorry, so this should be, the axis is there. This is actually 0 dB. And then a high pass does the opposite, where it will pass after it reaches a certain frequency, and then it will pass it. And then there's the last one is called a band reject. So it does opposite the band pass, where it will reject at a certain frequency. So it passes everything except a certain frequency. And that characteristic Bode plot looks like this one, where it comes and then it will go down and up. So it looks opposite the band pass filter. All right, questions about those different filters? Okay, so I've given you an example of like, oh, this is an application of when you would want to use this band pass filter, where you want to just send one specific frequency to go through and remove all the rest of the noise. It can get kind of tricky though if your signal is really close to the noise values. So there are some limitations on how well it does. All right, okay, so now let's move into like, okay, we want to solve this circuit. How do we even go about doing that? So we need to get an expression for the output in terms of the input. We will convert this to 1 over CS. I like to use S because it looks easier when I'm manipulating the equation, and multiplying by S is easier to me than doing it by j omega, but you can also keep it in j omega form, whichever one you feel comfortable doing. So 1 over CS, and then we get to treat this like a resistor. So this is called an impedance. Impedance acts like a resistance. So we treat it just like we would a resistor. So the word for the 1 over CS is impedance. So impedance. And we usually use like Z. So we'll use the variable Z instead of R. So R is for a real valued resistance, and Z will mean that it's an impedance, which is, treat it like a resistor, but it has a complex component to it. So it has that J in there. Or S. S is equal to j omega. Okay, so how would we solve this circuit to get an equation for V out here? If that element of a capacitor is a resistor, do you guys recognize this circuit? We want to find the voltage across this, right? So with trying to find the voltage across that, what circuit is this? It is an RC circuit. But if you're treating that capacitor like a resistor, you have a resistor there, and a voltage source, and you're trying to find the voltage across it. I heard somebody say it. Starts with a D.
Voltage divider.
Thank you, yes, voltage divider. So we're dividing the voltage across each element, and we want the voltage across the capacitive element. So it would be Vn times, oh my. And then to get the transfer function, all we do is divide over the Vn portion of it. So this would be our expression for the transfer function. The only thing we need to do to get it in terms of omega is to substitute S is equal to j omega. So then from there, it would be V out over Vn. So this would be our expression. So now we would be like, okay, I want to draw this Bode plot and understand what happens when I now have very different, I have a whole variety of frequencies. So to be able to do that, we have to do a couple things. One is to get it into what we call standard form. So standard form is that each element is a number times S or a number S plus 1 quantities, or just a number by itself. So in this we have 1 over kind of each quantity. So we want to get this bottom quantity, we need to get into a form of like number S plus 1. So to do that, as I said, I like to work with S's. So I'm going to go back to this one. And I'm going to multiply the top and the bottom by 1, which would be CS over CS. And then that's going to allow this to cancel. And then it will cancel on this one. And my expression then turns into 1 over 1 plus RCS, or 1 over 1 plus RC j omega. And this would be considered my standard form. From there, last time we kind of started this. In order to find magnitude, I would need to take the magnitude of this expression. So I'm going to have to do this with omega j in there because I know how to take a magnitude when I have a plus bj. So remember, a plus bj, when you take that magnitude, gives you the square root of a squared plus b squared. So now it's going to give us v out over vn is going to give us the square root of 1 squared plus r squared c squared omega squared. And this is now a function of omega. And so I can pick omega equals some value and then find the answer for that one value. So let me just pick. So omega equals 1. I plug it in. I get 1 squared plus 100k squared plus 0.04 micro squared and 1 squared. So that's going to yield some value. I don't have it figured out right now. At omega equals 10, I would do the same thing. And I could plug in a whole bunch of numbers of omega, and I would get one specific plot on the graph. So this is going to be, I'm just going to write this out so you have it in your notes. Like, oh, okay. Sorry, this is not a plus. So these are multiplied, 0.04 microsquared and 1 squared. So these are all going to be in volts per volt. So when we solve the circuit, the default unit will be volts per volt that we find. Then we would need to convert it over to dB, and then we would graph it on a graph such as this. So on the x-axis is a log, and y-axis is normal. This is called a semi-log. It's called the semi-log graph. So at 1, I found one specific value. So say it ended up being that value there. Each of these lines, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have the big jump, and so this will be 20, 30, 40, 50, 60, 70, 80, 90, and then 100. It's hard to read that. Make that a little bigger. So this will be 100. This will be 1,000. So each one has a multiplication of 10 on the graph. So these are called a decade between each one. So what will this value be? Thank you. And the next one? Yep, 100,000. Oh, I cannot write that way. Okay, so on this, as I said, I found one value at 1. Let's see, what was 10? And 10 is there too. And I could plug in 2 and I could get a value for 2. I'd find it to be this one. I already know the form of this, and we'll go through how I found the form in the next step. But I would have to do this for every single omega to be able to create this graph. And then I could connect these dots. Let's see, where does it change? At 250. So this is going to go out here till I reach about 250, and then it's going to start to change and go down. So on this, that was kind of difficult to find. Like, I would have to take a lot of time to find each variable or each value for each omega. So is there a quicker way? And yes, there is. So that's what we're going to jump to next. Looking at this Bode plot, though, this is the magnitude Bode plot. What is this? What type of filter? Thank you. So this is a low-pass filter. So yep, this would be what I would expect for a low-pass filter. And this is called the straight line approximation method that we're going to go into next. And it is going to give you at a very specific point, it starts to move. Once it changes, if it's decreasing, it will be by 20 dB per each decade. So at 250, if I'm at 0, and then at 250, then this would be 2,500. It would be here. And then the next one would be here. So these would be, each one would be less by 20. With a straight line approximation, we know that we're going to find that this value of 250 at that critical frequency, these are called critical frequency or break frequency. We actually know that the actual frequency is 3 dB less if it's going down, and it will be 3 dB above if it's going up. So instead of at 0, it's actually minus 3 dB. And then we know that this goes down by 20 from that point. So this would be minus 23 dB. And then at this point, you're going to be at what value here? So these are So these are separated by a decade each. So if this value is minus 23, what will be the value below?
43?
Correct. So you can label these on the graphs. So how do I know that it goes down by minus 20 dB or up by 20 dB? So that's kind of the next step. So
Is it always 20?
Uh-huh.
Or is there a reason why?
Yes. So if you plug in the values of omega after a change,
Okay, yeah.
you'll actually see it's always a plus 20 for what we call a zero and always a minus 20 for a pole.
Is it from the same person? That, like, or I think, I'm guessing that it's from like when we convert like decibels to like gain.
Yeah.
And it's, okay.
Yep. So when you convert that from volt to volt to dB, and then you have no change or effect from a polar zero, it's because of the square root, and then we're taking the quantities in there. So as long as you're not near a critical frequency, those terms are very negligible, and then it always stays constant at that slope.
Gotcha.
There's situations where if your poles and zeros are really close together, that's hard to gauge what exactly is going on. But if they're far enough apart, then it's really easy to use this straight line approximation. All right, so one other thing to note, 20 log base 10 of 0 is undefined. So we never do the graph right at omega equals 0. So you're always going to pick omega equals some small value. Usually if you can start at 1, that's always easy and nice to start at 1, but if not, you can go to 0.1, 0.01, 0.001, 0.0001, 0.00001, you know, and something that's close to below any of your poles or zeros. So I said the word polar zero. So a pole and a zero depend on this standard form. So I'm going to back up. So the first step is to get into that standard form where you have a number s or a number s plus 1 or just a number by itself. So this is the first step once you've solved the circuit, is you get in standard form. And then once you get into standard form, it looks something like this one. So the top part, which is the numerator, are going to be what you call zeros. And the bottom are your poles. And the next step after you've determined the standard form is you determine what these values are. What I mean by zeros is its roots at the top and the roots at the bottom. So if I have a quantity that's just s in the top, that means I have a 0 at the origin. If I have, let's go back to this one. And J, omega, I'm missing my C in here too, RC. So this value, if you multiply it out, the R and the C is 250 plus 1. And so I like to look at it in the form of RCS. It's a little easier to solve for the S quantity there, which would be a negative 1 over RC. And that would be considered my root. So that's when that quantity is equal to 0. So you guys see why that's negative 1 over RC? Okay. So that value of negative 1 over RC, in this case it would be negative 1 over 250, is the value of my critical frequency, and in this case it's in the bottom, so it will be a what? A pole or a zero? A pole, thank you. So you would say I have one pole at 250, or 1 over 250, sorry. Nope, I'm sorry, this was 1 over 250. This is 250, so it is 250. Sorry. So what RC is point something, and then it goes into 250. Okay. So you take those poles and zeros, and then you find a omega that's less than that. So in that case, it was omega is equal to 250, so I can do omega equals 1 and find a starting value. So you want to find a starting value. So you're going to have to do that square root calculation, but you only have to do it for one number, which is really nice. So you just do it for that one number. That gives you a starting value. And then the nice thing about this is that you can add these by superposition, basically each effect of a polar zero. So for a constant term, there's no frequency change, and so we know from magnitude of a constant, it's just going to be the same, the magnitude of constant. So you take 20 log of that, and it's going to be a fixed value over frequency. For a zero, you're always going to have a plus 20 dB per decade change. And for a pole, it's always going to be a minus 20 dB per decade change. So if these are just at the origin, so they just continuously go down and up at a slope of 20 dB per decade. So you just have to find on the graph, where is that going through? So you find a point it goes through, and then you know that the slope goes through that point. If it's a zero, it's going up. If it's a pole, it's coming down. For the quantities so this is just in S alone. This one is when we have an S number plus 1. So for S equal to -1 over a number, the negative just means it's stable or not. That has to do with our phase. So we're always looking at the magnitude of this. So it's just going to be 1 over some number. And that number then corresponds to a point. So it's going to not have any effect until after that number. If it's a zero, again, it's going to change by 20 dB per decade. And if it's a pole, it will decrease by 20 dB per decade. So this is kind of the summary of increasing or decreasing. Zeros are always plus, poles are always negative. FC denotes critical frequency. Or you'll hear it be called the break frequency. All right, so let's look at this one. So this 50 is a amplifier. So out of that amplifier, with it having just a single input, this is going to be 50 times Vs. So this is similar to what we just did, except for the elements are in different locations. So again, this is going to be 1 over CS. I'm going to treat it like a resistance. So what is, my VR is located here. What is VR going to be? My equation for VR. Anyone? What do I consider my voltage here?
50 VS.
Thank you. 50 Vs. And what element am I trying to find this across? It will be across the resistance, so this one will have 10K on the top and then 10K plus 1 over CS. So doing the same thing, multiplied by CS on the top and bottom. So now I have the term on the top, except for I need to divide by VS. So divide that by VS, and now I have my equation. And so 50 times 10K times 0.2 micro. And so to find, so what do I have? What does this top information tell me?
0.
Okay, so I have a 0 at what? At 0, correct. So I call that the origin. So 0 at origin or 0 at 0. What does this tell me? Correct? Uh-huh. And is this a polar or 0? Thank you. So bottom is pole. So I have a pole at a 1 over, and again, I don't write the negative just because I'm taking always the magnitude. So 1 over 10K times 2 micro. So when omega equals this, or j omega equals this, so this value is 500 radians per second. So I've determined, I put it into standard form, I determined my poles and zeros. Now I want to look at, like, where do I start drawing this on my graph? So I have a pole at 500, 0 at the origin. So the poles and zeros that are not at the origin, I want to just take an omega less than that and find that one value. So I'm going to pick omega equals 1. And then I'm going to have 50 times 10K times 0.2 micro times 1. So I do plug in the omega, and then it's going to be over the square root of 10K times 0.2 micro times 1 squared, so this whole quantity squared plus 1 squared. And this ends up, I think this ends up being a minus 20 dB. So taking 20 log (50, 10). So this ends up being 10, and then 20 log of 10 gives me a, wait, 0.1, sorry. 0.1, and then this ends up being a minus 20 dB. So on my graph, I know at 1, so here at 1, I know a value, and this is going to be minus 20 dB. So then I look at, erase these. Then I know from there that it has the 0 at the origin. So what does that tell me? Anyone?
The first decade, is that 0?
So this is the one that says if I'm at a 0 at the origin, I have a slope, continuous slope. So going through that point, I'm going to have this slope of plus 20 dB per decade until I reach 500 radians per second. So here I know, like, okay, it's going to increase. So at 1, I'm going to be here at minus 20. So at 10, what value will I be at? 0. And then at 100, I'll be at 20. And so on until I reach, what was it, 500? Yeah, 500. So 500 is going to be 2, 3, 4, 5. So here's 500. So at 500, I'm going to be in between this point at 20 and this point at 1,000 would be at 40, and I'm going to be somewhere in between there. How would I find the exact value there? So I would plug omega equals 500 radians per second into that equation for the magnitude and go through that whole process again, take the square root, and I would get the exact value there. That exact value is going to show me that I'm going to be 3 dB less than what this approximation kind of shows. So kind of extrapolating out, like if I did go up there, I look like I'm about 3/4 of the way up. So maybe like 34, and then this might be like 31 or 2 dB. And then what happens at 500? What does this effect do?
Decrease the slope by 20.
Correct. So I add on to what the current slope is, a negative 20 dB. So it's going up by plus 20 dB per decade. Right at that point, it's going to then add on the negative 20 dB per decade, which will be 0. So that's why then it flattens out after that. And then there's no more poles or zeros, so the graph goes on forever at that value. What filter is this one? Thank you. High pass. Correct. Okay, questions about this? Okay. Ready to do another one? Okay. All right, does this look scary? How would I simplify this? What's the value here, first off? It's what?
Can you remove the C2 and the R2 because it's past that E out?
So you can't remove them, but what can I do? If I'm thinking of them as resistors, impedances, can I combine them? I can combine them as a parallel value, and I could call it maybe Z2. Same thing here. I could combine these as elements in parallel, and this would be, and call it kind of Z1, which then is going to simplify this to look, I'm going to simplify it even more. What's this value in front of the 10? What's the value at that blue dot? 10 VS, correct. So I can just say that this is 10 VS, and I have a Z1 element and a Z2 element. And this looks like just what I did, right? So this would be the parallel form. And if I'm trying to find V out here, this is going to be V out is equal to 10 VS Z1, or I mean Z2 over Z1 plus Z2. And I can plug in those values, and I already did the math for you on these. So get a common denominator, and then you're just going to manipulate this till you get down to a standard form. So from this, what does this mean? What does this top one mean? What do I have here? A 0 at? So to find it, you would set R1C1S plus 1 equal to 0 and solve that for S.
So it'll be at R1, 1 over R1C1.
Correct. So this would be a 0 at R1, 1 over, can talk. A 0 at 1 over R1C1. What does this mean down here?
R1 plus R2 over R1 times R2 times C1 plus C2.
Yep. So I have a 0 at one location and a pull at another location. So I have to find the starting value. So how do I find that? Here, let me grab what these are. So they are at 10 and 3. 1, 2, 3, 4, 5, and at 500 again. So this is at 10, and this is at 500.
So will the graph be given to us while we're solving this, or?
No, you have to draw it. I already had them done, so.
Okay.
So no, you have to come up with it from scratch. So
So we just have to guess those numbers to get there, essentially.
not guessing. I already calculated these out beforehand. So I just plugged in the values from the graph or from the circuit itself. So, oh, just kidding. I didn't give you the values. R1. I don't have them written down. So assuming that these values gave you the 500 and the 10.
Okay.
So you would have to know what R1 and C1 were. I thought I had put them down there. So to do this, I'm going to pick an omega. Omega equals 1 is before any of those two, 10 or 500. And then it's going to give me, and then I'm going to plug in the values for all of these. And same thing on the bottom. And that's going to give me a starting value, and it will give me 20 dB. And then it goes flat until I reach the first one. What happens at the first one? So what happens at 10?
Starts rising by 20 dB per second.
Correct.
Or decade, sorry.
Yep, so it's going to go up by 20 dB per decade. So I'm going to go from 20 to 40, and then at this one it would be up at 60. But I have another change before that time at 500. And what happens at 500? Thank you. Minus 20 dB per decade. So I add that on. I've gone up by 20 dB, so I add on the minus 20 dB. And that gives me back to 0, and then it will be flat. So this would be the graph of this circuit. All right, questions? You guys super excited for your quiz on Friday? All right, so homework is, one of them you have to do the signal, another one you have to do conversions, and then the rest are doing the Bode plot. So, fun, right? All right, see you guys on Thursday.